For the fall 2019 University of Pittsburgh Senior Industrial Engineering Capstone, we worked with FedEx Ground's Facility Maintenance and Material Handling Department on preventive maintenance. FedEx Ground is a major shipping company that provides 1 to 5 day small package delivery within the United States and Canada. Their facilities use systems of conveyors, chutes, trucks, and vans to successfully deliver more than 8.5 million packages per day on average.
FedEx needs help in optimizing how to best incorporate the use of handheld scanners with automated scanners in their North Pittsburgh branch. These scanners are used to monitor the vibration levels on the motor, gearbox, and bearings of their slider bed conveyors to identify when preventive maintenance is needed. The goal is to identify which bearings should be scanned, how often they should be scanned, and the time and cost savings associated with the scans. Prior research shows that analyzing the root mean square velocity in the z direction is optimal for picking up shifts. An initial visualization of the data is shown by plotting a time series of the readings. The PM schedule is overlain and is shown there is no apparent trend in the data. Because there is no indication of deterioration, a time analysis of time to failure is not possible.
With our initial visualizations showing a lack of trend within the data, we decided to move towards understanding the behavior of each component over the time span within the data, which ultimately led us towards building shoe-work control charts to establish process limits. Shoe-work control charts for individual measurements were applied on 2 machines, the GP1-1 and GP2-2. These machines had consistent readings and minimal outliers and were assumed to be representative of all slider bed conveyors. Prior to constructing their charts, an upper threshold was established. Speaking to our sponsor, there were instances of extreme vibrations caused by other equipment within the facility that compromised sensor readings, so these outliers were removed. With these bounds in place, we constructed accurate control charts. Multiple iterations of filtering points above the upper control limit were conducted until an in-control process was found. These bounds were then imposed onto the non-filtered data set in order to gain an understanding of how often a specific sensor obtained an out-of-control reading. For motor sensors specifically, lines representing ISO standard 10816 were also included. Using these charts, we calculated the probability that each sensor would obtain an out-of-control reading. Because there were no reported failures during the time in which this data set covers, these points are false alarms. They do not represent a true shift in the mean, but are a result of random variation. In estimating the likelihood of reading a false alarm, we could then move forward in analyzing how frequently a reading should be taken. Because a point above the control limit calls for action to be taken, it is important to minimize the probability of reading a false alarm while also maximizing the probability of detecting a true shift in the process. To understand this trade-off, we simulated taking a reading at different time intervals, mimicking the process of manually collecting a point over some regular interval of time. Finding an interval that maximizes the trade-off between reading false alarms and a true shift, while also minimizing the frequency to collect data points, is a key factor in our overall analysis. Using various time intervals to randomly collect a data point, each method was then plotted as a time series and was compared to its respective upper control limits. Our analysis concluded that in taking a reading once per month, the chance of reading a false alarm can be minimized while maintaining a high probability of detecting a true shift in the process.
Our decision tree is broken up into 2 branches that break off further based on the answers to the questions in each diamond box. For each scanner, if a point is above the upper control limit, we perform a visual check to see if any minor maintenance needs to be conducted or if any evidence of failure is present. If maintenance is performed, we then wait until the next day and record another reading. If that point is above the upper control limit once again, we then perform more extensive maintenance. If there are no points above the upper control limit for the automated sensors, we continue operations as normal, and for the handheld scanners, we wait to conduct our next set of inspections next month. It is important to note that in the automated sensor decision tree, the handheld scanner is used as a method of verification for the automated sensor reading.
Based on our analysis, we believe that continuing to use sensors to monitor the status of the equipment allows a decrease in preventive maintenance tasks. In terms of the measured improvement of our analysis, we compared the time and cost associated with preventive maintenance currently with what the time and cost associated with preventive maintenance would be after the implementation of our plan. In our plan, we were able to reduce the tasks involved in monthly maintenance from about 6.5 hours to a little over 3 hours. Due to this reduction in the monthly preventive maintenance tasks, our plan brings the total time of annual labor associated with preventive maintenance from 126 hours annually to 86.5 hours. and the labor costs associated with preventive maintenance from $1,889 to $1,296 annually. Subsequently, our plan decreases the labor costs associated with preventive maintenance by about 30%.
Based on our work, we would like to present FedEx Ground with the following recommendations. The first is that FedEx Ground should use automated sensors for all motors, gearboxes, and 2 critical bearings per machine. The second is FedEx Ground should conduct manual handheld scans once per month for bearings which are not monitored by automated sensors directly. Based on our analysis, bearings begin to produce out-of-spec readings consistently toward the end of each month before monthly maintenance is conducted. The third is that FedEx Ground should use defined statistical process control charts procedures to help monitor vibration levels and better detect out-of-spec readings. And lastly, FedEx should further investigate correlations between all bearings in order to maximize sensor resource efficiency. We would like to thank the following people for their involvement in making this project a success.